Hello everyone, my name is Gao Xixiao, the leader of the Group 7. Today, we want to talk about the article Safe Offline Reference Learning with Feasible Guided Diffusion Model, which has been received by the ICAR 2024. And next, let's welcome Jiang Hongyu to talk about the background of the article.
Good morning, everyone. My name is Jiang Hongyu. I will explain the background. I want to begin by highlighting the critical importance of safety in reinforcement learning, especially for real-world applications like autonomous driving, industrial automation, and healthcare. In these domains, a single policy failure is not just an error, it can lead to catastrophic outcomes. Traditionally, safe reinforcement learning is implemented using a framework called Constraint Markov Decision Process, or CMDP. These methods enforce safety constraints during training. However, they rely heavily on repeated online interaction, meaning the agent must constantly explore and learn in real or simulated environment. In many cases, this approach is impractical, expensive, or simply too risky. Offline reinforcement learning offers a safer alternative instead of learning by interacting with the environment. Offline RL learns policy from pre-collected data of safe action transitions. This approach avoids risky online rollouts, but it comes with its own set of challenges. Most existing offline safe RL methods only use what are called soft constraints. This ensures that, on average, the cumulative safety cost stays below a certain threshold. But in practice, this still means the agent can occasionally violate safety constraints at individual time steps. In safety-critical application, even a single violation can be unacceptable, so there is an urgent need for an offline RL framework that can guarantee hard safety constraints, meaning absolutely no safety violation at any time. Next, Ouyang Yifan will introduce the motivation of proposing the FISOR method in details. Thank you.
My name is Zhao Jinhan. I will introduce the part of integrating hard safety constraints into offline R presents several key challenges. First, feasibility determination is difficult because offline data consists only historical projections without any environment interaction. To decide whether a given state admits a safe policy under hard constraints, one must systematically evaluate the state space, but limited data coverage makes it hard to judge states absent from the dataset. Second, distributional shift and policy deviation become problematic. New policies must remain close to the behavior policy or risk unsafe actions in unsafe states. Yet, if hard constraints are too strict, the learned policy becomes overly conservative, favoring only actions nearly identical to those in the data. If constraints are too lax, the policy might choose risky actions. Third, optimizing three objectives: maximizing reward, enforcing hard safety, and minimizing divergence, where clear regularization from the behavior policy leads to a highly non-convex, multimodal, and conflicting optimization problem prone to instability and violation. There is a trade-off between expanding the feasible region and remain conservatism, relaxing feasibility, criteria or using complex estimators can enlarge the feasible site, but introduce estimation errors that misclassify unsafe state as safe, causing violations. Conversely, over-conservative feasibility estimation yield a tiny feasible region, limiting achievable return. Next, Gaoqixiao will introduce the part of methodology.
Okay, hello everyone. Today I will introduce the FISOR, a novel approach to reference learning designed to balance safety and reward effectively. Let's break it down into simple terms. First, the FISOR involves three key steps. The first one is identify the safe states. The second one is differentiate the objectives based on the safety. And the last one is extracting the final actions using diffusion model. Let's look at the first step. We started by looking at the historical data, previously recorded states and actions. Our goal here is straightforward. Identify where it's safe for the agent to take actions. How do we do that? We calculated something called the feasible value. If the value is 0 or negative, it means that at least one safe policy the agent can follow from that state. And if it's positive, there's no safe way forward. We estimate this feasible value using the regression method trained on the past experience. And for step 2, after identifying the safe states and the unsafe states, we handle them differently. For the safe state, the agent aims to maximize the reward. However, to prevent the risky decision, we ensure the new actions remain close to those observed in our historical data. Partially, we maximize the expected reward but introduce the penalty called KL if our policy drifts significantly from the previous behavior. And for the unsafe states, the shifts forward, minimizing the risk. The agent selects the actions that reduce the likelihood of enter dangerous scenario. And similarly, we constrain the policy to stay close to the historical data, avoiding the actions that might introduce the unnecessary risk. And for the last step, instead of using a traditional method, we approach action selection as a simply problem. We build an energy function from a data that assigns lower energy into the actions that we are safer and more rewarding. We then utilize a diffusion model. We started with a random actions with the pure noise, and through the iterative refinement steps guided by our energy function, we transform this noise into practical, safe, and rewarding actions. The diffusion model ensures our final policy effectively balance the safety and the reward by leveraging the strengths of the probability sampling techniques. And to sum up, the FISOR smartly integrates the safety and reward through feasibility analysis, the strange objective differentiation, and the innovative diffusion-based sampling, creating an effective, robust decision-making framework. Okay, thank you.
Hello, my name is Liyu Zhang. I will show you the dataset and the result. The paper evaluates its method using the DeepSafe-RL benchmark, which includes offline reinforcement learning tasks with strict safety requirements. These tasks include lane keeping, where the agent must stay within its line, and obstacle avoidance, where it must navigate safely through environments with static or moving obstacles. Other variant tests different safety rules, state dimensions, and action spaces. To assess performance, the authors use three key metrics. Safety performance is measured by zero violation rate, showing how often the agent avoids collisions or lane departures. Return represents the discount cumulative reward, capturing how well the task is completed. Robustness reflects the consistency across multiple random seeds and its initial conditions. The FISA is tested against over 10 baselines. In every task, FISA achieves a 100% zero violation rate, outperforming baselines in safety. It also obtains the highest or second highest return, especially in scenarios where safe action space is small, demonstrating that its feasibility-guided region helps maximize reward safely. Moreover, FISA is evaluated in offline imitation learning, where it performs strongly even without the explicit reward signals, maintaining both high safety and task performance. In terms of strengths, the study uses a realistic benchmark and shows that FISA balances the safety and performance effectively. However, it is limited by relying only on simulation without testing on real robot or high-dimensional inputs like images. It also lacks analysis on sample efficiency. Future work should explore deploying FISA on real hardware, extending it to image-based tasks, and evaluating its robustness across different dataset sizes and qualities.
Hello, my name is Liu Pingyi. Now let's move on to the insights. FISA tackles the major challenges in offline reinforcement learning by enforcing strict safety constraints. Instead of tolerating occasional safety variations, FISA guarantees zero variations by learning a feasible region from which the policy can operate safely. This approach doesn't rely on complex optimization frameworks, keeping the learning process simpler and more scalable. Moreover, it uses an energy-guided diffusion model for policy extraction, reducing the complexity of training. FISA offers guaranteed safety. With no variation across all test tasks, it extends to offline imitation learning and other settings with hard constraints. The framework is built on solid theoretical foundations, introducing a feasible value function and proving equivalence with weighted behavior cloning. However, the method isn't perfect. It depends heavily on the quality of offline data, and in rare cases, it may misidentify unsafe states. The diffusion sampling in high-dimensional action space can be computationally expensive. Additionally, FISA has only been tested in simulative environments so far. To address these challenges, documentation techniques can improve the coverage of feasible regions. Introducing hierarchical feasibility analysis could scale better for larger domains, and combining diffusion with other planning methods might reduce computational cost. Real-world validations, especially with robots or vision-based tasks, is crucial for moving FISA from simulation to real-world applications. In summary, FISA presents a clear and robust way of ensuring safety in offline reinforcement learning. While it offers significant advances in safety and generalizability, real-world challenges such as data sparsity and real-time constraints need to be addressed in future works.